Good afternoon, friends. Today I am going to discuss on the topic that is refining of metals. So before I am going into details, I would like to show you the contents. So these are the contents I am going to discuss. So let's start with the introduction part. What is extractive metallurgy? Extractive metallurgy is the branch of metallurgy that deals with the extraction of metals from their respective ore minerals and refining. And we should remember that this extraction and refining must be economical, eco-friendly, as well as it should be profitable also. So what are the impurities? Impurities are those elements which are present in a base metal during its extraction. The best example I can give that is impurities present in the iron during its extraction. Suppose I am extracting iron, but I will create iron with other elements like carbon, sulfur, phosphorus, manganese, and silicon. So you see, during extraction of iron, I am getting iron plus these other elements within it. So these are the impurities. And this is the base metal. So likewise, there is an example if I give in case of copper. While I am extracting copper, I get copper plus some impurities like iron, tin, and some oxygen will be there. And as an example, is like extraction of zirconium. While extracting zirconium, I will get zirconium in addition with some another element that is hafnium. So it is very difficult to get a pure metal during its extraction process. Always there will be some other elements with it. So now the question is, now the second part is what are the sources of impurities? So if you see the basic source of impurities are the ore itself, or you can say the raw materials used for extraction are the basic source of impurities. Like during extraction of iron, the iron ore, hematite, magnetite are the source of these impurity elements. And other sources are like from the environment, the metal absorbs some impurities, like some dissolved gases will be always there, like oxygen, nitrogen and hydrogen will be there in the metal during extraction. And some impurities come during the processing of the metal. After extraction, when we are doing processing, some impurity will come. And some impurity will come during handling and during transportation, like that some impurity will come. So let's, I will go to what is the need of refining. Already we discussed that impurity will be always there in the metal. We cannot get a 100% pure metal. The first reason of doing refining is that the impurity elements impacts an adverse effect on the different properties of the metal. Like it has an adverse effect on the physical property of the metal, chemical property of the metal, as well as the mechanical property. For example, if I go for mechanical property, impurity impacts adverse effect on the hardness, strength, and the ductility. And suppose I am talking about physical properties of the metal. It hampers the melting point, boiling point. It affects the electrical conductivity, thermal conductivity. And if I am talking about the chemical property of the metal, it affects the corrosion resistance and oxidation resistance, and sometimes its reactivity. And the second important point is why I should go for refining. That is, some impurities have economical value. I mean, they have particular application, they have particular use. So we need to separate those impurities elements from the base so that we can use it in another process. So now come to this part. What is the principle of refining? This is very important part. But I am not going into the thermodynamics principle of the refining. I will just say the overview part. Like, suppose I am principle of refining is I have to send the impurity element present in the base metal to an another phase. So I allow the impure metal to come in contact with this extracting phase. This one is the extracting phase. So when I allow this impure metal to come in contact with this extracting phase, and this extracting phase is such design that the impurity element will go into this part, because when it will go into this part, the chemical potential of the impurity element will be lower as compared to here. That means initially I am having metal with other impurities, the chemical potential of the impurity here is high as compared to this one. That's why it will migrate from here to here. And this part is called extracting phase. The best example of extracting phase is your silicate slag. I can give you a during extraction of metal metals or made to form a slag, that is actually silicate. So always during extraction the impurity element joins this silicate slag. That means during extraction two phases will be forming. One is your metallic phase and another is your non-metallic phase. Or this I can say this slag is a non-metallic phase. Because in this slag the chemical potential of the impurity element will be lower as compared to that of metal. But one important point is that we cannot go for 100% purity. Even if we try to purify a metal, we cannot produce 100% purity metal, because this is against the thermodynamics part. The entropy will not allow it to produce 100% purity. Suppose for example, during extraction I am getting 98% purity metal. That means I am having 5% impurities in it. So when I reach up to 98%, for example, I am getting after purification, that is refining. After refining, I am getting 98% purity metal. That means I am having 2% impurity in it also. So to go from 98 to 100% is very difficult. This from here to here is easy. But from going here to here it is very difficult. And the second extracting phase, the best example is your vacuum. Sometimes we go for vacuum process. So vacuum like for degassing, like during extraction of iron from steel or during refining of iron to get steel, I will having some dissolved oxygen in it. So if I will go for vacuum, I can extract or I can separate the oxygen from the steel. So I can produce the pure steel. So next I will go to this part. So this part is over. All this part is over. I will go to this part, basic approaches of refining of metal. So basically if you see, there are three basic approaches. The first basic approach is like during extraction of metal. While extracting metal, we will give such a thermodynamic condition and kinetic conditions so that the metal will form a separate phase and the impurities will form a separate phase. That there will be no mixing of them. And second approach is like for reactive metals. Suppose I want to extract some reactive metals out of it. So like for example zirconium, titanium, these are some extract reactive metals. So always we have to go for an intermediate process. That means I will produce a pure compound out of this reactive metal from its source. Then from this pure compound I will go for a pure metal. So I cannot produce directly pure metal. I can produce the first pure compound. From this pure compound I will go for refining. And third approach is always, this is the main approach we are doing in the industry. We are producing bulk metal which contains large amount of impurities. Then we will produce and we will go for purification or refining. So these are the three approaches we go. Now come to this part, that is refining methods. If you see, there are major three refining methods. One is physical method of refining, second one is chemical method of refining, and third one is electrochemical method of refining. part, physical method of refining. So these are the various physical methods of refining: sublimation, selective distillation, crystallization, liquefaction, selective dissolution, Gion refining. These are the various refining physical methods. If you see in the physical methods of refining, we do not go for any chemical reaction. There will be no chemical reaction for refining. Only there will be a physical separation of the emitting elements from the base metal. So these are the points, or these are the principles that we say for physical methods of refining. That means difference in the boiling point, that is the emitting elements to the different boiling point is compared to that of the base metal, and all this. So now let's start with first sublimation. So in case of sublimation, suppose I am having a compound A and B. These are the two liquid compounds, compound of metals A and B. So if the compound A will having high vapor pressure, and B is having low vapor pressure. So just by heating this at a low temperature, the A will become vapor, and B will remain as a liquid. So I can separate the compound A from B by just. So I can separate A from B by just taking the solution of A and B, because it will just vaporize and it will remain in form of liquid. So I can collect the vapor and I can condense and I can make pure water. So next process is that is selective distillation. Selective distillation is somewhat similar to this method. Here it depends on the boiling point of that. That means A is having low boiling point and B is with high boiling point. Already this is more volatile. This is less volatile. So I am using a container with A and B. A is a compound, B is compound. I want to separate this by this selective distillation method. And I can see here A is low boiling point. I can say this is having more volatile. B is high boiling point. So this is very volatile. So when I will heat this mixture of the solution, then at lower temperature, A will just vaporize and I can condense it. I can separate it. Then comes to crystallization. So here this crystallization method is similar to that of precipitation. That means it depends upon the concentration as well as temperature. Suppose I am having a mixture of sodium chloride and potassium chloride, and I want to separate potassium chloride out of sodium chloride solution. So if I will increase the concentration of this potassium chloride in this whole solution, or if I will just decrease the temperature, then potassium chloride will convert into solid. It will crystallize into solid rather than sodium chloride. So I can separate the potassium chloride out of sodium chloride by this method. Then comes the liquefaction. Liquefaction is a very important method, especially used in the industry. Like suppose, and this liquefaction refining depends upon mainly the melting point difference. Suppose I am having an error of iron and tin. Generally during extraction of tin, the tin contains 10% of iron. So it is forming an error of iron and tin. So it is very difficult to separate the iron out of tin. So it is forming an error. So I want to separate, or I want to produce pure tin out of this error. of iron and tea at temperature of, let's say, that is 400 degrees centigrade. Then what happens, since steam is handling low melting point, that is only 327 degrees centigrade, its melting point, and iron is 39 degrees centigrade melting point. So just by heating this alloy at 400 degrees centigrade, I will melt all the tea because it is just higher than that of this temperature melting point. But iron is very high melting point, so it will not melt. It will just remain as a powder. So I can easily separate this. So now by this equation defining, I can separate copper out of zinc and all. Due to difference in the melting point. Now how to selective dissolution. This method depends upon the solubility. Like for example, I am having lead. Lead contains some silver. I want to separate silver out of lead. If I will add zinc in the molten form into the molten lead, so what happens? The solubility of silver is higher in zinc as compared to that of lead. So if I add molten zinc into the solution of this, then this silver will go into the zinc and it will form a separate phase out of this phase. So I can separate the silver out of it by this method. Now come to zone refining. Zone refining is this method is also called zone melting. Zone refining is a very important method in the laboratory scale because it is very expensive, and this method is carried out especially for semiconductors because ppm level of impurities in the semiconductor will affect its conductivity, electrical conductivity. So in this method, we will take a thin section of a semiconductor, for example. Suppose this is silicon or germanium. Any of the models I will take, and I will take a circular one. I am having a rod of impure rod of silicon or germanium, and I take a circular coil. If I have to move either one of them, either I will have to move this circular coil across the cross section, or I will have to move this rod. I have to keep one constant and I have to hand. Suppose I will move this coil from this end to this end. So suppose this coil is initially here, for example. This is a heating coil. So what happens? This will start melting. Just stew, not totally melt. It will just stew. It will become liquid. But this whole part remains solid because coil is already on. So what happens? When this coil moves further, this part, suppose now the coil is here. So this part becomes liquid, become molten, but this part started solidifying. So the impurities will go from here to here because we know that the solubility of impurities is higher in the liquid phase as compared to that of solid phase. And further when the coil moves over here, so now this part will become liquid and this part started solidifying. So impurity will move from here to here because obviously because the solubility of impurity will be low in case of solid. So solid will reject the impurities like this. So in this way, the impurity will get rejected from solid to the liquid. Suppose the coil is now here, last solid part. So this becomes molten state and finally it will solidify. All the impurities come to this end because this part will solidify later at the end. So I can cut this part and throw it. By this way, if I will pass the coil various times, 4 times I Now come to chemical methods of refining. जो physical refining जो now come to chemical methods of refining. Here, in case of chemical method of refining, some chemical reactions are occurring. So here what happens? We have to add some refining agent into the impure method, impure voltage method. So this refining agent will react with the impurities preferentially as compared to that of base method. So when this refining agent will react with the impurities preferentially, forms a compound and it will form a separate phase to that of the base method. The example of refining agents are oxygen, chlorine and sulfur. Basically in the industry we are using oxygen as a refining agent. For example, in case of steel making, if I see in case of steel making, I am having iron with other impurities like silicon, phosphorus, manganese. So if I add oxygen, what happens? The oxygen will preferentially react with the silicon to form silicon oxide, manganese with manganese oxide, and like phosphorus pentoxide like this. So this oxide will form a separate phase out of the iron. Now I can separate it. So this process is actually oxidation process. Likewise, if I add chlorine, it will form chloride and form a separate phase. If I add sulfur, it forms sulfide. There is no sulfation, it forms separate phase. Likewise. There's another example I can give is refining of copper, that is called fire refining. If you see, the copper contains impurities like iron, arsenic, bismuth, various impurities are there. If I add oxygen, so oxygen will preferentially react with arsenic, bismuth, iron to form oxides, and copper will remain there. So I can separate the copper out of these impurities by this method. Now I will discuss refining for intermediate classes. Here the impure metal was created in glass phase. To form a gas phase. In the second phase, this gas phase will decompose to give pure metal plus gas phase. So this decomposition may be either by cooling or by heating, depend on the process. This one is the best example I can give is the purification of nickel. In case of nickel, the impure nickel is reacted with carbon monoxide to form nickel carbonate. This is a gas phase. This is gas phase. And when this nickel carbonate is prepared at high temperature, the temperature here is above 200 degrees centigrade, and this one is only 40. So this nickel carbonate, when it is above 200 degrees centigrade, will decompose into pure nickel and carbon monoxide. This is the example of this. Now we will discuss the Behera method. Behera method is similar to this method. It is used for refining of zirconium especially. Here zirconium, impure zirconium react with two iodines to form zirconium iodide. This zirconium iodide is decomposed to zirconium plus iodide. So here impure zirconium is initially reacted iodide form zirconium iodide, and this zirconium iodide decomposed to pure zirconium iodide. So this is the Behera method. Now we will discuss the last part that is electrochemical method of refining. So in case of electrochemical method of refining, we have to use electricity. Here we have to make the impure metal as anode and pure metal as cathode, and we have to take it in electrolyte cell and electrolyte. This may be aqueous electrolyte or maybe cold electrolyte. So when I am passing the current through this whole circuit, what happened? The impure anode started dissolving. It go into the electrolyte solution and it further decompose the deposition of this metal properly. So it gets totally dissolved and the thickness of the cathode will increase. I will get a pure metal. This is actually a commercial method which is used for purification of various metals. If I want to purify reactive metals like aluminum, so I go for molten electrolyte. If I go for purification of gold, copper, then I will have to choose aqueous electrolyte. So this is all for today. So we have enjoyed the video. Thank you.